Hello, everybody, and welcome to our next session. It's about high-performance persistence with WebSphere Liberty and InstantOn. So I'm Markus Kett. I'm CEO and co-founder of MicroStream, and this is a shared session together with Mark Stoodley from IBM. So I'm super proud to be in the session with you, Mark, and also with Richard Fichtner. Actually, sorry about that. Richard is sick. But Mark has prepared a demo. So this will be very interesting. And so this is about how to run MicroStream and EclipseStore cluster. But actually, this is more not about how MicroStream works. So we do a little short intro, but it's more like how you can benefit from InstantOn and what InstantOn actually is and how it works and how it helped us to run MicroStream cluster. So I worked with my team with Java for almost 20 years now. We built Java IDEs and yes, several open source projects. And so with MicroStream, we are now an Eclipse project. So we are super proud to announce that MicroStream is now EclipseStore. And we start with a short introduction to what actually EclipseStore is, how EclipseStore cluster works, and what the challenges are with EclipseStore cluster, and how we were able to solve it with the WebSphere Liberty InstantOn, and how you can benefit from this great feature. So all of these modern applications, of course, they need max performance, lowest data storage cost, and everybody wants fast implementation, fast time to market. So these are the normal requirements for modern applications, right? But in practice, it's not that simple. But we believe with Java, we have the perfect programming language because of it's extremely fast. We are able to execute everything in memory in microseconds, microsecond response time. We have a great JIT compiler. And if you have questions about how JIT compiler works, ask Mark. So he's the guy who writes the code with his team. So this is your chance to ask everything you want to know about how JVM works and how you can make it faster. So the JVM even can outperform C programs. So this is really great, great news. We have GraalVM native images to accelerate applications. But in this talk, you will learn why we don't need GraalVM native images anymore. So the programming language is awesome. And also we are able to handle all kind of data with Java. So we can deal with all data types, all data structures. So we can use JSON. We can store simple lists. We can deal with great complex graph structure. So everything is possible. Also with vectors. So they are super important for this new AI stuff, right? So we can do everything with Java. And we can search in memory with Java Streams API. And searching and filtering the streams is very fast. In comparison to the database, it's around 1000x faster. So we talk about we talk about microsecond query time when we talk about the performance of Java in memory. So this is around 1000x faster than a comparable database query. And now with EclipseStore, we add persistence to Java. So the initial idea is persistence is complex. And actually, I want to focus on business logic, on writing applications with Java. I don't want to care for persistence. Actually, the environment should care for persistence. This was our vision. And this is now what EclipseStore provides you. And there are three benefits. So performance, as I mentioned, in combination with EclipseStore, your application and data processing will be 1,000x faster than comparable database queries. And we are able to save up to 97% cloud data storage costs. And implementing is simple because it's pure Java stuff. So EclipseStore is now a final release. You can download it via Maven Central. The final release was released on Monday. In time, just in time for JCon. Let's jump into more detail. So here we can see a traditional architecture. Here we have an application or a microservice written in Java. We are used to use Hibernate for object relational mapping or data conversion when we use a NoSQL database. And mostly we use a local cache to accelerate database queries. So with Java, everything is great, but with databases, they work fundamentally different from Java, so they are slower. We talk about millisecond response time when we talk about the performance of databases, no matter which database we are using. And it's not only the database, so it's also how we convert the result set into objects again. So, and this is really slow. And in terms of pricing costs in a cloud, databases are very expensive. Here is an example. 250 gigabyte PostgreSQL as a service costs you around, depending on a machine, around $5,000 per year. You can have this a little bit cheaper if you choose a smaller machine, but the more nodes you need, the higher the price will be. So this is very expensive. And because of the databases, they introduce their own database-specific data structures. They are limited to a specific use case. So if you have a microservice architecture and you have to consume completely different data and deal with different data structure, structured data, unstructured data, sensor data, complex graphs, you need multiple and different database systems. To accelerate database queries, very often distributed caches are used, and on top of that, many users use searching servers to speed up your searching. So multiple clusters are used, and this is actually the main reason why the cloud costs are so high and why cloud costs are skyrocketing. So multiple clusters for running only one big data application in the cloud. So how we change this? So now with EclipseStore, we replace object relational mapping or a data conversion, because we are now able to store objects as they are in a memory. So we just serialize the objects into any data storage. Because we keep data in memory, we use the object graph in memory as an in-memory database. So we can skip the local cache. And we are now able to store objects in any data storage, in any binary data storage, by using the Eclipse serializer. So we can use cloud object storages like AWS S3, for instance, and they are really cheap. So 250 gigabyte AWS S3 costs you only $78 per year. So this is almost nothing. And the cloud provider cares for everything. So this is really great. And we, with EclipseStore, we combine so the power of Java with lowest data storage costs in the cloud with object storages. You can also use plain file storage, for instance. This is also possible. In distributed environments, here is an example. We replace the common application cluster, the distributed application, with an EclipseStore cluster. So we are now able to replicate EclipseStore applications or microservices through hundreds or even thousands of JVMs. So we run the EclipseStore cluster. Everything is already in memory. We replicate the memory, so we can skip the caching cluster. We store data directly in a cloud object store. We can deal in Java with all data types and data structure. So we only need a cloud object store, super cheap. We remove the distributed caches and searching also. And so we simplify the whole architecture. That's great. And this is pure Java stuff. You also can run an EclipseStore cluster only for searching or caching, and so accessing an EclipseStore cluster by using REST, by any applications. You can also build your application with Kotlin or Python, or use stateless services to query an EclipseStore cluster. So this is also possible. This is the recommended stack. So this is a really great combination: EclipseStore with microstream cluster. Mark will tell about more about Open Liberty and OpenJ9, of course. So with microstream, we now provide, as I mentioned, EclipseStore cluster and a fully managed service. So this runs also in already in production. You can check this out. The main features here are, so you don't have to deal with Kubernetes. So you can just set up and run a cluster very easily with some clicks. And we provide horizontally scaling, scale to 0, fully managed cloud service. So this is great, but there are also some challenges, and there are a lot of challenges for us. So this is how it actually works. So normally this is clear, but let's see how it works. Horizontally scaling means if your load goes up, then your system is in trouble. So now actually you want to run, you want your system to automatically start up additional nodes to distribute the load, to be more cost efficient, to provide fast response time. So your system should scale out automatically. And in case the load goes down, you also want to scale in your system and scale it into almost 0. So if there is no load, there are no costs. And again, if the load goes up, then you want to scale out your system again. So this is actually what the goal is, what we want to have. So our problem was with our cluster, we were in trouble because of scaling out was not that easy. Why? It's because of starting new cluster nodes took from 12 seconds up to 35 minutes. And this was really a problem for us. The reason for that long startup time was there is an EclipseStore needs some time to initialize the objects in memory. So here we have a delay, and this can be super expensive. And additionally, we had some problems with JVM startup time or chip warm-up time, and so this really hurt us. Then we tried to solve this with so there are some approaches, so different approaches how we could solve this. Solution number one was just run static nodes. So let's provide a cluster where you just choose how many nodes you want to run. So, okay, if I run 3 nodes constantly, everything is fine. But if the workload goes up, then your system is in trouble. But okay, that's it. So that's the problem. If the load goes down, then 3 machines are running, but actually you will burn money. So this is not cost efficient. And if the load, if there is no load, then your machines will constantly run, and we will burn a lot of money. This is not a great solution. This is not elastic scaling, and this is not scale to zero. So what should we do? Solution number 2 was starting nodes in advance. How does it work? So of course, everything is AI today, machine learning. So why not adding some machine learning stuff to EclipseStore cluster? Okay, then we can assume that in some minutes, probably the load will go up. So let's start machine in advance. So we have some more time, and if really a load goes up, then our cluster will be prepared. That's great, and this will work, and this works great. But the problem is, if the assumption is wrong, then so then the workload will be distributed through multiple machines. Actually, it's not needed. So we will burn money again. And if the assumption is wrong because of the load is much higher than we expected, then our system is in trouble. So then response time will be low, and so we have delays and very expensive latencies. So this is not a great solution. This is actually not what we wanted to provide. Solution number 3, GraalVM native images. So with GraalVM native images, now we would be able to create a native executable, and it's much faster startup time. So it promised much faster startup time. So we checked this out. The problem with GraalVM native images for us, and the challenge was there are really many challenges because of you cannot use all Java features. Reflection is a problem. So ahead of time compilation leads to longer build times and so on. And it's really complicated stuff. So we were not really happy with using GraalVM native images in production. So final solution was WebSphere Liberty InstantOn. So because of with WebSphere Liberty On, we were now able to store the hot JVM state and restore the hot JVM state on starting nodes, and this accelerates startup time and tremendously. And now with WebSphere Liberty InstantOn, it's really true. So our cluster nodes are able to start instantly. So great name. And so at this point, I like to hand over to Mark. So he can now explain how this works, how this what InstantOn actually is, how it works, and how you can use it for your systems. Mark, the stage is yours.
Great, thanks, Marcus. Let me just get my slides going here.
And if you have some questions, please use the chat. So we try to answer all technical questions.
All right, so just a quick intro about myself. So I work at IBM. I'm a senior technical staff member there, and basically I've been building JIT compilers and Java virtual machines for a little over 20 years. So I've been working on IBM's Java-based runtimes that we build for our products and stakeholders and make available for everyone to use. I'm currently the sort of lead technical person for all of the runtime technology work that happens at IBM for Java. So just a little bit about Liberty, since Marcus has mentioned that it's part of the things. If you haven't looked at Liberty recently, I'm not here to sell Liberty, but I just wanted to give you a little bit of background. It's an application server framework, very lightweight. It's an open source project. If you've only learned about WebSphere application server, I really encourage you to take a look at some of the things that Liberty can do, because it's a very different kind of form factor for building microservices for building cloud native apps, for building microprofile, and even Jakarta EE apps. It's a very flexible framework. And it's the one that we're going to be talking about today as a background. So I just wanted to give you a brief introduction to that. Also, underneath Liberty, we're going to be running a JDK that's produced by IBM called IBM Semru Runtimes. If you haven't heard of Semru before, Semru is the name of the tallest mountain on the island of Java in Indonesia. So I like to say it's the part of Java that's in the clouds. And IBM Semru runtimes are really designed to work very well in the cloud because of some of the performance capabilities that it provides. But just to give you a basic idea of what it is, we take the OpenJDK class libraries and we replace the Java virtual machine inside with the Eclipse OpenJ9 Java virtual machine, which is the Java virtual machine that IBM built and has open sourced now with the Eclipse Foundation, and we've been working on that as an open source project for about the last 6 years now. So it's available for all kinds of platforms and runs really, really well because we've built things like the InstantOn technology that I'll now talk to you about. So InstantOn is a capability that we built into both Semru and Liberty. So it's a sort of combined facility here, which is designed to provide really ultra-fast startup. And it uses the Linux CRIU, Checkpoint Restore in User Space library, which is a library that's been around for about a decade. And the sort of improvements that we were looking for from InstantOn is sort of that we've demonstrated I'll give you a very quick demonstration up here of some of the, on a variety of different kinds of apps, from very simple things that have almost no payload whatsoever to more advanced kinds of heavier workloads. You can see that startup time can improve by a dramatic amount. So we usually say it's somewhere in the ballpark of 10 to 18x improvement in startup time, and even first response time can get accelerated quite dramatically. Markus has already thankfully gone through the comparison against some of the reasons why we built this technology rather than leveraging something like the Graal native image approach. And basically, I'll highlight on kind of the most important one here, which is the full Java support. So Graal native image, because it has to limit dynamic class loading and therefore, understand things as Markus mentioned around all uses of reflection, and some tools don't work very well with native image in deployment mode. We didn't really like that as a full solution for production workloads, and so we've designed this InstantOn technology as a sort of alternative to provide really very fast startup as a good comparison point against what native image is able to do. And so the basic idea here, just to sort of depict it a little bit graphically here, is in your development environment, in your build CI, you're going to go through a step where you build a checkpoint. You're going to start your application, go to a certain point, checkpoint it, and then you're going to distribute that checkpoint along with your app to your production environments. And then in the production environment, you just have to do the restore. And as Markus mentioned, the full app comes back, the app server comes back, the hot JIT compiled code comes back, etc. And then you have a full JVM from that point forward running whatever is actually running in your application, whatever workload is being handled. So you can react to new workloads, new phases that come in your application. You can interface with it with all the regular Java tools that you're used to, etc. So let's dive a little bit more deeply into what this and how this works. So as I mentioned, it builds on top of this CRIU Checkpoint Restore in User Space library. I'm going to go through a sequence of slides here where I have kind of the stack on the right-hand side. I'm just going to go from bottom to top and explain a little bit about how things work. So CRIU is basically a facility that operates at the operating system level. It's aware of what resources and can find out what resources a process is using, and then it can checkpoint and save the resources that are being used by that process and store it to disk, and then you can restart in another place and resuscitate basically all of those resources so that the process can continue running. It's a very low-level facility. There's lots of hard edges and hard corners that you can get in trouble with. So it's not really something that you would want to use directly from Java as a way of getting fast startup for your Java applications. And that's the purpose of some of the higher layers here. So the next layer up is the Semru JDK. And so we've done work here to make the facilities of that native CRIU library available to Java applications to be able to use. So similarly to how CRIU is aware of the resources and things that the process needs, the JDK is aware of the things that you've allocated in your process, the connections that you've made, etc. And it also provides facilities for being able to register things that need to be added to the checkpoint or kind of remembered about the checkpoint, and then to do compensation work or to execute basically hooks on the restore side to recover the state of what those resources need to do. And it's a very flexible service. Again, it provides a lot of flexibility, but with flexibility comes complication. And so at this point, we haven't actually GA'd the InstantOn technology at the Semru level. It's there, it's available for people to use. But like we say, it's a little bit complicated to use because there's so much flexibility available. It's good for managing what's going on at the JDK level, but there's still some complexity here. I'm going to talk a little bit more about that as well in the next few slides. But let's keep going up the stack. Oops, up the stack, not down the stack. So the next one up is the Liberty InstantOn technology. So I mentioned that there's a lot of flexibility at the Semru JDK level that makes it a little bit harder to use. At the Liberty level, we've basically tried to resolve that problem by simplifying the interface, how people would use this checkpoint restore facility. At the Liberty layer, basically all you have to do is say, there's only a couple of options for where you can choose to do your checkpoint, and that dramatically simplifies how things are going to work. The first option is that you can take a checkpoint before applications are initialized, which means basically you're checkpointing all of the work that Liberty, the application framework, has to do in order to get to the point of initializing applications. And the advantage of that is that no application code is run, so we're aware of all the resources that have been created on behalf of Liberty, and we can manage all of those resources ourselves internally. That means all you have to do is restore and start initializing your applications, and there's no danger that something that you've initialized will be inadvertently added to a checkpoint. The second point is that you can set a checkpoint after the application is initialized, and here, we might need to be aware of some of the things that your application is doing, but because mostly what you're doing is relying on facilities of the application server can still automatically register all of the hooks that are needed. And in most cases, you don't actually even have to do anything. You can still just start your app and it will work just fine. Liberty will capture all of the resources that need to be checkpointed and need to be compensated on the restore side, and things will just work. And that means, finally, at the application level, you don't actually have to do anything. The only thing you have to do is decide which one of those two checkpoints you want to do. So let's talk about some of these things that need to be compensated for, just to give you a flavor for what that all is. So basically, because you're taking the checkpoint in your build environment, the checkpoint environment, that might not be the same environment as where you're going to restore this process in your production environment. The machine types might be different. The number of cores might be different. Definitely the time is going to be different. And so all of these are things that the JVM and Liberty need to be aware of when you restore a process in the restore environment. You're going to have to update all of these things so that the Java application isn't aware that it came up in a restored checkpoint, as opposed to running, having started from scratch in the restore environment. And so on the right side, just some examples of things that might have to be updated, right? So your network configuration might be different, the machine configuration might be different, etc. And so all of these things are taken care of by the InstantOn facility so that you don't have to worry about them. Excuse me. Now, some other interesting things that come about when you're trying to do this is that there are some aspects of the JVMs in the restore environment. Because you're restoring the JVM from a single checkpoint, you still want to make sure that different restores of that checkpoint look unique. In particular, you want random seeds to continue to be random. You don't want every JVM to come up running in the same with the same random number seed, because you still want them to behave as if they have different random number seeds. Also, there are some interesting aspects of security that need to be taken care of in making sure that you're not, sacrificing the security of the restored JVMs. And again, this is something that Semru runtimes and Liberty are taking care of for you. So I mentioned there's a couple of places to checkpoint. What are the trade-offs involved in those two things? So on the right-hand side here, I've kind of depicted, the sort of basic startup process and how long things take. Excuse me, I'm sorry. And as you can see, there's a bunch of work that happens up until the point where Liberty is going to begin initializing the applications that are installed as inside its framework. It has to do a bunch of work. And if you can checkpoint there, you can then applications could be initialized. You could then choose to checkpoint after applications are initialized, and from that point forward, the server is up and is ready to accept requests. So, what are the trade-offs between these two points? Well, obviously, the later you checkpoint means the faster you can get to this accept requests. If I checkpoint after app start, then I'm basically ready to accept requests almost immediately. Whereas if I did it before the app start, and I still have to start applications and then I can accept requests. So it takes a little bit longer to get up and off the ground. On the other hand, there may be some more resources that I have to deal with if the application is allocating resources that need some of these compensations in the restore environment. Then the hooks need to be registered for those things appropriately. And there are cases where the application may register or may use a resource that Liberty or Semeru is not really aware of, and therefore the hooks might not get created, and the application might have to do work. And so the risk of that happening is obviously higher the further up you go. So, but you always have this sort of safe checkpoint level. If you have to, you can always go back to before app start, and things will just work. All right, so current status is this has been GA'd in Liberty for work on Linux x86. It's been tested on a couple of the cloud services. As the other clouds advance their Linux kernel levels, they'll be able to take advantage of this right now. Basically, these clouds have kind of already advanced to the point where you can use sufficiently advanced kernels to be able to make this work. And in Kubernetes, it's actually very easy to deploy these things. There's just a couple of extra facilities that you need to grant in order to be able to leverage the facility, the CRIU facility at the operating system level appropriately. From a Liberty standpoint, not all of Liberty has been annotated at this point to be able to do checkpoints, but there's quite a few. Excuse me. There are quite a few of the features that have been enabled for use with InstantOn. If you happen to leverage a feature that has not yet been enabled for InstantOn, a failure will occur in your build at the point where you request a checkpoint. So it's not, you can't get into trouble in your runtime environment. You will always know whether or not the checkpoint is at a valid state or not. There are a few known issues. I'm going to skip through these because I have to get to the demo. I want to show you guys how this all works. But basically, there's a couple of things that we've been working on, and these are things that, over time they're going to get better. We're working through these right now. Actually, some of them I think have been dealt with already, but we're in the process of fixing all of these things as we find them. And we're always looking for sponsor users. So please, if anybody wants to get involved with us and try this out and explore collaborating like we've done with Markus's team, we'd love to talk to you about that. All right, so I'm going to switch to a demo now. Hope everyone can see that. So I've got two machines here in my cloud environment, and I'm just going to show you. So I have some scripts that I'm going to run. So basically what I'm going to do is I'm going to show you starting Liberty without using a checkpoint, and then I'm going to show you starting Liberty with a checkpoint, and we're going to compare the startup times that we see with that. So this is the script that I use to build the default app server, and you can see it's quite simple. It's going to use this default Docker file. So let's just look at what that default Docker file is. It's also quite simple. This is all based on Java 11 using one of the Open Liberty containers that's available on our container registry. This is all just filling in stuff. the main point down here is there's a configure.sh script, which is going to get run by Liberty to initialize itself and get ready to going. In the default case, this isn't going to do anything extra. It's just going to, it populates a shared class cache, which does provide some startup benefits, but not on the scale of what InstantOn is able to do for you. But it's basically pre-populating a shared class cache, which has some JIT code and some classes in it. And it's going to start the app server in a fairly efficient way. So I'm going to just start that process while I continue on this other one. So let's just get that going, because it's going to take a little bit. And then I'm going to look at what's going to happen on the other side. So if we're doing InstantOn, it has a very similar build process. It has a few extra options that we have to pass in, kind of those abilities, those capabilities that we have to add into the Docker process in order to be able to run the checkpoint restore in user space. Remember, these are things that happen on the build side, so they happen inside your CI environment. And it's going to use this InstantOn. I can't see what I'm doing anymore. Okay, let's do it this way. Let's do InstantOn Docker. Okay, so you can see this is all same thing, Java 11, Open Liberty container. All this is different. Sorry, all of this is the same. The only thing that's different here is that we're going to run this checkpoint.sh, and we're going to use after app start. So we're going to use the later of the two checkpoints that I described earlier. And that's the only difference in the script. The whole rest of the script is exactly the same. And as you can see, that one over there has already finished. So let's get the InstantOn one building. Now we can start looking at what we're going to do when we run this thing. So let's go back to the left-hand side here, and we're going to look at the default run script. So the way that we're going to run this is it basically just starts the container, right? It's going to open up a port. I'm not actually going to show the app servers running today, just to save a little bit of time. But excuse me, as you can see, it just runs the default demo, and then I can show you what the InstantOn run will. In contrast, on the InstantOn side, we do still have to add a couple of checkpoints in the run on the run side to make things work. But for the most part, this is all a very similar type of environment. Like you can see, most of the options here are actually just the same. We've just added a few capabilities here to be able to restore the checkpoint. All right, so we're done over here. So I'm just going to start one of these and see how long it takes. Sorry. So we're starting the default Liberty server here, and it's going to take a little while. There we go. So it started in about 4.244 seconds. So let's just do that again to make sure it wasn't a fluke. Although I know it's not, because I've seen this time before. So 4.1 seconds. So we're starting at basically a little bit more than 4 seconds if we run with the default server, and then if we instead use InstantOn to run, that's virtually instantaneously. So it starts in 0.209. That's 209 milliseconds that it starts in. So let's just check to make sure that wasn't a fluke. 0.231. You can see it takes longer to stop the server than it does to start it. 203 again. So we've basically taken something that took 4 seconds, and we've managed to make it start now in about 200 milliseconds. So that's about a 20x improvement in startup performance. And basically all we had to do was add that additional line into our CI step and a few extra options on the run side. So this is actually very easy to configure, very easy to use. As I said, we're always looking for people to come and join us and try this out. And basically that's all I have to present today. Markus, were there any closing words that you wanted to say as part of this?
Yes, of course. So in terms of Instant Liberty, WebSphere, InstantOn, and EclipseStore, this is a great combination. What we are now running on with our cluster solution, and we're currently working on an integration also with Open Liberty. And also the usage of OpenJ9 is a great fit with EclipseStore. So if you have any questions about how to use it, so you can contact Mark directly, or even us to share experience and to answer questions. And about the EclipseStore cluster, you can learn more about tomorrow, because I want to invite you guys to join us tomorrow at the EclipseStore Summit, which is also a part of the JCon Online. You can see in the chat there are actually no further questions. So this is your chance to ask technical questions. So obviously, no technical questions.